Networking means managing secure and reliable communication between different systems and services. In simple words, it allows computers, devices, and applications to connect and share data efficiently and safely. Today, we'll be learning some important networking concepts. Basic terminology, topology, OSI layer, protocols, subnet DHCP, DNS, NAT, PAT, CDN. Let's understand what a network is. Node-to-node connectivity for data communication is known as network. It is a set of devices, nodes, connected by communication links. Some important terms related to communication and networking. Communication. It means the transfer of information according to agreed conventions. This can include hand signals, language, Morse code, or even smoke signals. Next is data communication. This refers to the transfer of data from one or more sources to one or more destinations. Then we have telecommunication. It is communication that happens over a distance. Examples include telephony, telegraphy, and television. And finally, network communication. This is a network of data processing nodes that are interconnected for the purpose of data communication. 5 key points on a data communication system. Message, the actual data or information to be communicated, text, audio, video, etc. Medium, the physical path through which data travels, cables, fiber optics, wireless signals, etc. Receiver, the device or computer that receives and interprets the message. Protocol, the set of rules that govern how data is transmitted, received, and understood between devices. Sender, the device or computer that generates and sends the message. Data can be represented as text, numbers, images, audio, or video. Now, let's look at data flow. It shows how data moves between devices. In simplex, data moves in one direction only. In half duplex, it moves both ways but one at a time. And in full duplex, data flows in both directions at the same time. Network topology refers to the structure or layout of how computers, devices, and network components, like routers, switches, and servers, are connected and communicate with each other. In simple words, it shows the arrangement of devices and how data travels within the network. It refers to the way in which a network is laid out physically. It is a geometric representation of the relationship of all the links and linking devices to one another. Mesh topology. Every device has a dedicated point-to-point link to every other device. A fully connected mesh network has N1, 2 physical channels to connect N devices, with each device having N1 I/O ports. An example of a mesh topology. Suppose we have 5 devices, that means N equals 5. The number of physical channels will be 5 times 4, divided by 2, that is 10 channels. And each device will have 4 I/O ports to connect with the others. Now, let's look at the benefits. Mesh topology provides redundancy and reliability. There are multiple paths for data to travel, so even if one link fails, communication can continue. It also offers high performance, because direct connections lead to faster data transfer and lower latency. However, there are a few drawbacks. It's complex and costly. As the number of devices increases, the number of connections grows quickly, making it harder to manage. And it's not very scalable, because adding a new device means creating new connections with every existing one, which is difficult in large networks. Each device has a dedicated point-to-point link to a central controller, usually a hub. Less expensive than mesh, star topology is one of the most commonly used network topologies in computer networking. In this structure, all devices, computers, printers, servers, etc., are connected individually to a central device such as a hub, switch, or sometimes a router. The central device acts as a communication controller for the entire network. Now, let's look at an example of a star topology. Imagine an office with 4 computers, A, B, C, and D, all connected to a central switch. Each computer has its own dedicated cable running to that switch. This means any communication, for example between computer A and B, goes through the central switch. Now, let's discuss the benefits. It's simple and easy to manage. Each device connects directly to the hub. If one cable or device fails, it doesn't affect the rest of the network, and the faulty device can be fixed easily. It's also scalable. Adding a new device is as simple as connecting it to the central hub. However, there are a few drawbacks. The central hub or switch is a single point of failure. If it stops working, the entire network goes down. And it can become a performance bottleneck if too many devices send data at the same time, which can cause congestion and slower performance. Bus topology. One long cable acts as a backbone to link all devices. Multi-point connection, shared link, an example of a bus topology. Imagine a small office with 4 computers connected along a single coaxial cable. Each computer taps into this main cable to send and receive data. When computer A sends a message to computer B, the data travels along the bus. All devices can see it, but only computer B processes it. Now, let's look at the benefits. It's cost-effective because it uses less cabling compared to star or mesh topologies. It's also simple to set up and extend. You can easily add a new device to the existing bus. However, there are some drawbacks. It has a single point of failure. If the main bus cable breaks, the entire network stops working. It has limited scalability. As more devices are added, performance can drop and data collisions may occur. And finally, troubleshooting can be difficult, especially as the network grows larger. Ring topology. Each device has a dedicated point-to-point connection only with 2 other devices. A signal is passed along the ring in one direction. Example of ring topology. Imagine a small office with 5 computers, A, B, C, D, and E, connected in the shape of a ring. When computer A wants to send data to computer C, the data travels through computer B before reaching C. Now, let's look at the benefits. It allows efficient data transfer, as the data packets follow a fixed path, reducing the chances of collisions. It also provides predictable performance, because each device handles only a portion of the network traffic, keeping the flow consistent. However, there are some drawbacks. It has a single point of failure. If any device or connection breaks, the entire network can be affected. Also, there can be latency, since the data must pass through multiple devices before reaching its destination. Comparison with other topologies. Bus topology is cost-effective and simple but has limited scalability and a single point of failure. Ring topology offers efficient and predictable performance but can be disrupted by a single device failure. Star topology is easy to manage and scalable but relies heavily on a central hub. Mesh topology provides high redundancy and reliability but is complex and costly. Redundant topology. Redundant topology eliminates single points of failure. Redundant topology causes broadcast storm, multiple frame copies and MAC address table instability problems. Host X sends a broadcast. Switches continue to propagate broadcast traffic over and over. What is OSI Layers and Protocols? OSI Layers. The OSI model is a framework that explains how data moves across a network through 7 layers, ensuring smooth and standardized communication between devices. Protocols. Protocols are the set of rules and standards that govern how data is formatted, transmitted, and received across networks. The OSI reference model and the TCP/IP conceptual layers. The OSI model has 7 layers, each with a specific function. At the top, we have the application layer, which includes protocols like HTTP, FTP, and DNS. This is where users interact with the network. Next is the presentation layer, responsible for formatting, encrypting, and compressing data, using protocols like SSL and FTP. Then comes the session layer, which manages sessions and connections between systems, using APIs and sockets. The transport layer ensures reliable data transfer through protocols like TCP, UDP, and SCTP. Next, the network layer handles routing and addressing, with protocols such as IP and ICMP. The data link layer manages data transfer between devices on the same network using Ethernet or PPP. And finally, the physical layer deals with the actual hardware transmission, like cables, fiber optics, and wireless signals. Now, when we compare this to the TCP/IP model, it has 4 layers: application, transport, network, and network interface, which combine the functions of the OSI layers into a simpler structure. Both models describe how data moves from one device to another, layer by layer, ensuring smooth and reliable communication across networks. Protocols and port numbers. Protocols. In DevOps, networking are standardized rules that define how data is transmitted between systems. Port numbers. act as unique identifiers that direct network traffic to the correct service or application. Protocols and port numbers. Ports 20 and 21. File Transfer Protocol, FTP. FTP is for transferring files between a client and a server. Port 22. Secure Shell, SSH. SSH is one of many tunneling protocols that create a secure network connection. Port 25. Simple Mail Transfer Protocol, SMTP. SMTP is used for email. Port 53. Domain Name System, DNS. Port 80. Hypertext Transfer Protocol, HTTP. HTTP is the protocol that enables the World Wide Web to function. Port 443. HTTP Secure, HTTPS. HTTPS is the secure and encrypted version of HTTP. All HTTPS web traffic goes to port 443. Port 110. Post Office Protocol, POP3, is the most commonly used protocol for receiving email over the Internet. Port 3389. Remote Desktop Protocol, RDP, is a Microsoft proprietary protocol that enables remote connections to other computers. MAC address. A MAC address is a unique identifier assigned to the network interface card, NIC, of a device. It helps in identifying devices on a local network, LAN, and ensures that data is sent to the correct destination. It's like a digital fingerprint for your device. No two devices in the world share the same MAC address. What is a MAC address? Format. A MAC address is typically a 48-bit number represented in hexadecimal format, split into 6 groups of 2 digits, separated by colons or hyphens. For example, 001A, 2B, 3C, 4D, 5E. Uniqueness. Each MAC address is unique to the device's network interface, ensuring that no two devices on the same network segment have the same MAC address. Structure. First half, organizationally unique identifier or WI. The first 3 pairs of the address, 24 bits, identify the manufacturer or vendor. For example, 001A, 2B could identify a specific manufacturer. Second half, network interface controller specific. The remaining 3 pairs, 24 bits, identify the specific device or interface. For example, 3C, 4D, 5E is unique to that device. Function. Identification. MAC addresses are used to identify devices on a local network. Communication. When a device wants to communicate with another device on the same network, it uses the MAC address to specify the destination device. Visual representation. Imagine a network switch with several connected devices, each having its unique MAC address. When data is sent from one device, the switch uses the MAC addresses to direct the data to the correct recipient device. Example. Device A, MAC 001A, 2B, 3C, 4D, 5E, sends a data packet. Switch receives the data packet and reads the destination MAC address. Device B, MAC 001A, 2B, 6F, 7G, 8H, is identified as the recipient. Switch forwards the data packet to device B. In this scenario, device A, MAC 001A, 2B, 3C, 4D, 5E, sends a data packet. The data packet travels to the central switch. The central switch reads the destination MAC address 001A, 2B, 6F, 7G, 8H. The central switch forwards the data packet to device B, MAC 001A, 2B, 6F, 7G, 8H. Benefits. Uniqueness. Ensures that each device on a network can be distinctly identified. Efficiency. Facilitates efficient communication within local networks. Drawbacks. Static nature. MAC addresses are fixed and cannot be easily changed, which can be a limitation in some scenarios. Privacy concerns. Because MAC addresses are unique, they can be used to track devices across networks. IP address. An IP address, Internet Protocol address, is a unique numerical identifier assigned to each device connected to a computer network. It functions like a digital home address, allowing devices to locate and communicate with each other over the Internet or a local network. IP address. An IP address, Internet Protocol address, is a unique numerical identifier assigned to each device connected to a computer network. It functions like a digital home address, allowing devices to locate and communicate with each other over the internet or a local network. IPv4 address. An IPv4 address is a 32-bit address. The address space of IPv4 is 232 or 4,294,967,296. Represented in 4 blocks of 1 byte each. Subnetting. Subnetting is the process of dividing a large network, IP address space, into smaller, more manageable subnetworks called subnets. It helps improve network performance, enhances security, and efficiently utilizes IP addresses by organizing devices into logical groups. In networking, IP addresses are divided into different classes. A, B, and C are used for unicast communication, while D is for multicast and E is reserved for special use. Each class has a specific IP range and default subnet mask, helping networks identify hosts and manage traffic efficiently. In IP addressing, the network address is identified when all host bits are set to 0, and the broadcast address when all host bits are set to 1. For example, in a Class C network like 192.168.1.0, the network address is 192.168.1.0, the first host is 192.168.1.1, and the broadcast address is 192.168.1.255. This helps define how data is routed within the network. Types of subnet. 1. Fixed-length subnet. 2. Variable-length subnet. Fixed-length subnet. When a block of addresses is divided into subnets all having an equal number of addresses, this type of subnetting is said to be fixed-length subnetting. Variable-length subnet. When a block of addresses is divided into subnets, all having a different number of addresses according to your needs, this type of subnetting is said to be variable-length subnet. Now let's understand the concept of fixed-length subnetting with an example. We're starting with a Class C network having the IP address 192.168.1.0 and a default subnet mask of 255.255.255.0. In binary form, this mask is written as 11,111,111.1111111.1111111.000000000. Here, the last 8 bits, or the 4th octet, are used for hosts. Now, we'll take 1 bit from the host portion to create subnets. So, the 4th octet becomes 10 million. This changes our subnet mask to 255.255.255.128. Notice how 1 bit has moved from the host side to the network side. Now let's calculate. Number of subnets equals 2 to the power of n equals 2 to the power of 1 equals 2 subnets. Block size equals 256 minus 128 equals 128, which means our subnets will be: first subnet, 192.168.1.0 to 192.168.1.127. Second subnet, 192.168.1.128 to 192.168.1.255. Finally, the number of valid hosts per subnet is calculated as 2 to the power of 7 minus 2 equals 126 hosts. We subtract 2 because one address is reserved for the network address and one for the broadcast address. So, in summary, by borrowing 1 bit from the host portion, we divided our network into 2 subnets, each capable of supporting 126 valid hosts. Classless addressing, also known as VLSM, solves the problem of wasted IP addresses caused by fixed classful blocks. It allows variable length address allocations, making IP usage more efficient. CIDR, or classless interdomain routing, has largely replaced traditional classful addressing in modern networks. In this example, we're distributing a Class C IP block, 192.168.1.0, into 3 subnets based on host requirements. Subnet 1 supports 20 hosts with the address 192.168.1.32/27. Subnet 2 supports 8 hosts using 192.168.1.48/28, and Subnet 3 supports 2 hosts using 192.168.1.52/30. This method ensures efficient use of IP addresses based on network size. In this exercise, we're designing a subnetting scheme using variable length subnet masking, or VLSM. Each network has specific host requirements. For example, Net A supports 14 hosts using a 28 mask, Net B and Net support 28 hosts each with a 27 mask, while smaller networks like Net C and Net D use 30 and 28 masks respectively. This efficient allocation ensures that each subnet has just the right number of IP addresses without wasting any. DHCP. Full form is Dynamic Host Configuration Protocol. DHCP is a network management protocol used to automatically assign IP addresses and other network configurations, like subnet mask, gateway, and DNS, to devices on a network. What is DHCP? Dynamic Host Configuration Protocol. The Dynamic Host Configuration Protocol is a network management protocol used on Internet Protocol networks for automatically assigning IP addresses. How does DHCP work? DHCP DORA process stands for the following message flows between the client and the server: discover, offer, request, acknowledge. The DHCP process consists of 4 main steps that allow a client to automatically receive an IP address from the server. In step 1, the client sends a DHCP discover message to locate available DHCP servers. In step 2, the server replies with a DHCP offer, providing an available IP address. Next, in step 3, the client sends a DHCP request to confirm acceptance of the offered IP. Finally, in step 4, the server responds with a DHCP acknowledgement, officially assigning the IP address to the client. This process ensures efficient and automatic IP configuration across the network. DNS. The domain name system, DNS, is the phonebook of the Internet. Humans access information online through domain names, like google.com or youtube.com. Web browsers interact through Internet Protocol, IP, addresses. DNS translates domain names to IP addresses so browsers can load Internet resources. DNS on the Internet. On the Internet, the domain namespace, tree, is divided into 3 sections. Generic domains, country domains, the inverse domain. Generic domain, cont. A generic domain, also known as a generic top-level domain, GTLD, is the part of a website address that comes after the last dot in a domain name, for example, .com, .org, .net, or info. Country domain. The country domain uses the same format as generic domains but uses 2-character country abbreviations, e.g., S for the United States, PK for Pakistan, in place of 3-character organizational abbreviations at the first level. Second-level labels can be organizational, or they can be more specific, national designations. The United States, for example, uses state abbreviations as a subdivision of the U.S., e.g., CA.US. Popular records. Address, A, record, used to map a host name to an IP address. AAA record. The AAA record specifies the IP address, IPv6, of a host. Canonical name, CNAME, record, forwards one domain or subdomain to another domain, does not provide an IP address. MX record, directs mail to an email server. SPF record identifies the mail servers and domains that are allowed to send email on behalf of your domain. NS record, a name server, is a type of DNS server. It is the server that stores all DNS records for a domain, including a records, MX records, or CNAME records. Inverse domains. An inverse domain is used to map an address to a name. For example, a client sends a request to the server to perform a particular task, and the server finds a list of authorized clients. The list contains only IP addresses of the client. The server sends a query to the DNS server to map an address to a name to determine if the client is on the authorized list.